So dear students, after this module, you shall be able to understand the properties of the hypothesis testing, also identify its implications and assess the fitted econometric models. Let me introduce the subject of hypothesis testing to all of you. Fitting the regression line is only the first and a very small step in econometric analysis. In applied economics, we are generally interested in testing the hypothesis about some hypothesized value of the population parameter. Let's say we have a random sample denoted as x1 to x2 to xn of a random variable x with PDF or population or probability density function f as a function of x given mu. Regression analysis helps us to obtain the estimate of mu, say mu hat. Hypothesis testing implies deciding whether mu hat is compatible with some hypothesized value mu 0. To set up a hypothesis test, we formally state the hypothesis as a null hypothesis H0 as mu equal to mu 0 against an alternative hypothesis H1 which is denoted as mu not equal to mu 0, where H1, as I said, is called the null hypothesis and H1 is known as the alternate hypothesis. The question now is what does this hypothesis mean and what does it imply? Let's understand this. So let's start with the random variable x, that is x distributed normally with mean mu and variance sigma square. Now suppose we define our null hypothesis to be, as we defined earlier, hypothesis H0 is equal to mu 0 and mu not equal to mu 0 as the alternate hypothesis. So how do we proceed in such a situation? To proceed, the first step is to draw a sample from the population X and calculate its mean, which could be denoted as x bar. I am sure all of you would be familiar with that. Now the value of this x bar, which is obtained from repeated sample, will be normally distributed with mean mu 0 and variance sigma square by n. Now this is an inherent assumption which we generally make in our hypothesis testing. For estimation, this assumption of normality is not required, but for inference we have to make this assumption. Now null hypothesis being true resonates with the above explanation. Now such a distribution with the null being true is shown below with the help of the diagram, where you may find on the x-axis we are taking x bar. We have different values of this mean, which is sample mean x bar, and on the y-axis we have the frequency density function of x bar. And based on our assumption of normality, we have drawn this diagram, as you can see, which is a normally bell-shaped curve with the mean value mu 0. Now this distribution we are assuming is having a mean value equal to mu 0. So I am sure all of you are familiar with normal distribution and you can identify this shape of the normal distribution. Now if this mu hat is a good estimator of mu, which is population parameter, then it will take a value close to mu. That basically means that mu hat minus mu will be small. I am sure you all understand this. So if the null hypothesis is true, then mu hat minus mu 0 is nothing but is equal to mu hat minus mu plus mu minus mu 0. And this should be small, as mu hat minus mu is small, and the second term, which is nothing but mu minus mu 0, is 0. If the alternate hypothesis is true, then mu hat minus mu 0 is equal to mu hat minus mu plus mu minus mu 0, and it should be large, as mu hat minus mu and mu minus mu 0 are not equal to 0. So small or large depends upon the distribution of the estimator. So basically we are looking at the distribution of the parameter under the null hypothesis and the distribution of the parameter under the alternative hypothesis. That is the underlying logic behind this kind of a explanation. So in this model which has been set above, we don't expect x bar to be exactly equal to mu 0 because x bar may take different values in different repeated samples. So there is no reason to deny the possibility, but the chances are very rare that x bar will be equal to mu 0. If the mean is far off from mu 0, then there are two possibilities. Either reject the null hypothesis or do not reject the null hypothesis. Either way, the decision will contain some element of error, which means rejecting a true null hypothesis type 1 or accepting a false null hypothesis type 2. We do not have any foolproof way of deciding this, but we have certain mechanisms by which it can help us to understand this decision-making process. So if the probability of the mean which lies far off from mu 0 is less than the level of significance, we can conclude to reject the null hypothesis. For example, if the probability is less than 5%, that is, it lies in the upper and lower 2.5% tails, as can be shown in this figure, then you will find the probability of the mean being 1.96 standard deviations away is just 5%. And you can see this with the help of our diagrams, which we are showing here in our figure 2, where we are showing you the decision rules. And we have the different distributions of x bar. We have the rejection region on the left hand side, we have the acceptance region in the middle, and again we have the rejection region on the right hand side. So we have the upper tail, we have the lower tail, and these two tail areas separately are equal to 2.5%. Combined together it is 5%. And these tails are basically in a way obtained or bifurcated from mu minus 1.96 standard deviation and mu 0 plus 1.96 standard deviation. So, and the source of these diagrams basically is from Dorothy, but I'm sure you all understand the implications of this. So let me say that the figure suggests that the null would be rejected if x bar lies in the shaded area. That means if x bar is greater than mu 0 plus 1.96 standard deviation x bar, or x bar is less than mu 0 minus 1.96 standard deviation of x bar, which basically means the same thing as I said earlier, where if x bar either lies in the upper region or it lies in the lower region of or the areas of rejections in both the upper tail and the lower tail, then we reject the null hypothesis. We can make a simple rearrangement of this expression, and it would lead us to x bar minus mu 0 upon a standard deviation of x bar greater than 1.96, or x bar minus mu 0 upon a standard deviation of x bar less than minus 1.96. Admittedly, we can term the left hand side as z statistics. Therefore, we reject the null hypothesis when modulus z is greater than 1.96. As mentioned before, the decision rule established above is not flawless. There may be some problems here which we can discuss and try to understand. So let's go back to our initial condition of hypothesis H0 being true. We are saying there is a 5% probability that x bar will lie far away from mu 0 in the rejection region, and that is why we said the area in the two tails is equal to 5%. It also means therefore that there is a 5% probability of type 1 error, which is probability of rejecting a true null hypothesis and is equal to 5%. The researcher has the liberty to settle the risk of type 1 error and accordingly look up the critical value, which means you can fix up this critical error or type 1 error probability at 5%, 1%, 10%, depending upon our objective function. To sum up, there are three possible outcomes. One is the correct decision. Second is rejecting a true hypothesis, which is known as type 1 error. And the third is do not rejecting a false hypothesis, which I am sure all of you know, we have defined it as type 2 error. Now, to be able to perform the test, we need an additional knowledge of the sampling distributions of the estimators. It will be impossible to perform hypothesis testing without this knowledge, prerequisite of which is the assumption that the error term is normally distributed. So given the following model as yi is equal to alpha plus beta xi plus mu I, it simply means that ui follows normal distribution with mean 0 and variance sigma square. That is normally distributed with 0 and sigma square. The principal reason behind this assumption lies in the central limit theorem, also known as CLT, and we can define this CLT later on. Referring back to the basics, error term is defined as all those factors that affect y but not included in the model due to non-availability of data, omission, etc. So we are saying there are different reasons that why we include this error term mu I. Now suppose these factors are random, then mu represents the sum of random variables. Hence, by applying CLT, we can undoubtedly impose normality assumption on the error term. Thus, we may say that this mu is distributed normally with mean 0 and variance sigma square. From this, basically, we derive the probability distributions of the estimators of alpha and beta. The estimators are in fact linear functions of mu, applying one of the properties of normal distribution, that is that any linear function of a normally distributed variable is also normally distributed. So which means that if mu I is normally distributed, all its linear functions would also be normally distributed. And this can be deduced as alpha hat would also be normally distributed with mean alpha and variance sigma alpha hat square. Similarly, beta hat is also distributed normally with beta as mean and variance as sigma beta hat square. Now with this background, we now set the foundation for hypothesis testing. So suppose we wish to test something about beta, as already mentioned, it follows from normal distribution, and therefore by standardizing it, we get z equal to beta hat minus beta upon standard error of beta hat, which is distributed as a normal distribution with 0 as mean and 1 as variance. So z is a standard normal variate. Now since sigma square is not generally known, therefore replacing the population estimator by its sample estimator, we get a new variable which comes out to be beta hat minus beta upon a standard error of beta hat. But now this is distributed as t with degrees of freedom n minus 2. Earlier we had the distribution as z, but now because of this substitution, we have the new distribution known as t distribution with degrees of freedom n minus 2. So hence we use t distribution to test the null hypothesis. The calculated value of t has different sampling distribution under the null and under the alternate hypothesis, being higher under the latter. A higher t would be consistent with the alternate hypothesis. Thus, a higher t would mean rejection of the null hypothesis. Some of the following examples intend to illustrate the theory which we have given above. Let's take the example as one, or first example. So suppose we have data on income and expenditure for 10 households given in this table or form, table 1, income denoted as xt and expenditure as yt. So we have yt for these 10 households starting from 90 to 150, and the corresponding expenditures are, you can see and read from this table, ranging from 80, 100, 120 to going up to 260. Using the formula for our beta coefficients, we calculate the values here, and this calculation is shown here before you, where we have first calculated yt minus y bar, similarly xt minus x bar, and et hat. Having calculated all these, we substitute these values for beta hat, which is defined as sigma xt minus x bar into yt minus y bar upon sigma xt minus x bar whole square, and we get the value equal to 0.45. Now similarly, one can find out alpha hat, because alpha hat is defined as y bar minus beta hat x bar, and we obtain the value 35.72. So sigma hat square is equal to sigma et hat square upon n minus 2, and this is equal to 98.98 on substitution of the values of et hat, and sigma et hat you can calculate from the last column of this table by adding all these values. Now variance of beta hat therefore comes out to be equal to sigma hat square upon sigma xt minus x bar square. On substitution of these values of 98.98 and of sigma xt minus x bar square, we get this value of variance of beta hat equal to 0.0030. So all these are simple calculations which you can do either manually or maybe by use of your calculators, simple calculators. By running through the necessary calculations, the next is to test if income and expenditure are related, and therefore our null hypothesis is mainly that hypothesis S0 is beta equal to 0. So we want to test whether income and expenditure are related or not related. Beta is equal to 0, then there will be no estimated relationship between income and expenditure. Our alternative hypothesis is beta is not equal to 0, and let me in a passing say that this is a two-tailed test. So we have the test statistics t, which we have seen earlier is nothing but beta hat minus beta upon a standard error of beta hat. From the calculations we can substitute the value of beta hat and of a standard error of beta hat, and beta is equal to 0. So what we obtain is 8.30. If the level of significance is 5%, then next step is to look out for the critical value at that level from T table. That is, we must try to find out what is the T critical value for 8 degrees of freedom. 8 is n minus 2, n for in our example is 10, therefore n minus 2 is equal to 8. Now these critical values from the table are equal to 2.306. So we can compare these critical values with the calculated value. What we find is that the absolute value of T exceeds the critical value, which implies that we can reject the null hypothesis, that is beta is significantly different from 0. In this case, the test is statistically significant. Hence, we can reject the null hypothesis. It simply means that the probability of the difference between beta hat and 0 is due to mere chance and is less than the level of significance, and thus can easily reject the null hypothesis. On the contrary, if the test is statistically insignificant, it implies that the probability of the difference between the estimator and the hypothesized value is more than the level of significance. Thus, we cannot reject the null hypothesis, which is also mentioned by Gujrati and Potter in their textbook of 2010. Let's take another example, where in this second example, we have the hourly earnings as a function of years of schooling. From this example, we have calculated the Anova Table, which gives us the regression of earnings. It gives us the source of variation, sum of the squares of variations, SS, degrees of freedom, and mean sum of the squares, MS. So you have so many, in a way, output here, which gives you different informations, including number of observations, the F statistics, the probability of this F statistics, R squared, adjusted R square, and root mean square error, or root MSC. Now, if you look at the lower half of the table, we have the variables, we have the earnings, and these earnings are a function of S and constant. We have the coefficient values, standard errors, T values, P values which are greater than modulus T, and we also have the 95% confidence interval. I'm sure many of you would be aware with some of these terms which we are using in this output. So in a similar manner, let us test if the level of schooling affects earning from this example. And again, our null hypothesis is same, which is as hypothesis is equal to beta equal to 0. And again, we are saying the alternative hypothesis is beta is not equal to 0. So consistently, we are making the same kind of hypothesis, so that we understand the basic testing of hypothesis under regression analysis. The intention is to reject the null hypothesis, as only then a relation between earnings and schooling can be established. So if we reject the null hypothesis, we would conclude that there is an underlying relationship between earnings and schooling. Otherwise, it will be difficult to substantiate this kind of a relationship. Now, T statistics can easily be again calculated by looking at the regression output, and we get the T value which is equal to 2.45 upon 0.23. So 2.45 you can see is the value of the coefficient in the first cell, and you can also see the standard error is given to be 0.2318, and using these values we get the calculated T value equal to 10.65. We know that if this T calculated is greater than T critical values at 1.96, which is 1.96 at 5% level, then the decision can be taken in favor of rejecting the null hypothesis. So the result which we obtain from this value of 10.65 decides in favor of rejecting the null hypothesis, and concluding that earnings are significantly affected by the level of schooling. The column next to T stats in the regression output above is also a useful mechanism to test the significance of the coefficients. This P value, or the probability value, is the exact probability of committing a type 1 error under the null hypothesis. The level of significance is the largest probability of making a type 1 error. So whereas P value is the smallest probability given T statistics. So if this P value happens to be smaller than the level of significance, because the probability of making the type 1 error is very small, we can safely reject the null hypothesis under that situation. This method has an edge over an earlier method, as it allows us to know the exact probability of making the type 1 error, and we need not go to the critical values and go to the T tables to find out these critical values. So in our example, the P value for schooling coefficient is 0. That is, the exact probability of making a type 1 error here is 0, and thus the coefficient will be significant at all levels. So this P rule is a very useful tool to test a hypothesis. Let us look at another example, example 3. Suppose in our example 1, we want to test whether marginal propensity to consume is equal to 1. I'm sure you all know what is marginal propensity to consume. It is basically the change in consumption as a result of change in income. So accordingly, our hypothesis would be set as null hypothesis is beta equal to 0, and our alternative hypothesis in this case would be that beta is less than 1. So what will be the t statistics? The t statistics in this case is defined to be equal to beta hat minus 1 upon under root of variance of beta hat, because we have standard error. Now substituting from our calculations, our numerator is 0.455 and the denominator is under root of 0.0030, and this on simplification comes out to be minus 9.96, and the critical value for 8 degrees of freedom is minus 1.860. So what do you think you would be concluding? We can see that is greater than the modulus critical value, so we reject the null hypothesis in favor of the alternative hypothesis. Let's now try to understand some of the one-sided tests. So far you have seen that our alternative hypothesis has been that beta is not equal to 1. However, in our previous example we said beta could be less than 1. So the third example was an example of a one-sided test. The decision to perform depends upon the question that we wish to answer. We shall see that one-sided tests reduce the risk of type 1 error. One way of reducing the risk in two-sided test is to perform the test at 1% significance level as an alternative to a 5%. The alternative hypothesis was set as mu not equal to mu 0, that is, it must be equal to some mu 1. For simplicity, let mu 1 is greater than mu 0. Therefore, we will find null hypothesis now could be defined as mu equal to mu 0, and alternative hypothesis now could be defined as mu equal to mu 1. At 5% level of significance, if x bar lies in the upper or lower 2.5% tail, we reject the null hypothesis. Now, given the assumption x bar should lie in the upper tail, now this would also be compatible with the alternative hypothesis if it is true. On the contrary, if it lies in the lower tail rejection region, the test would suggest to reject the null, although the probability of x bar lying there should be 0, given the assumption which we have made. So thus in such a case it would be logical to accept the null, which is reject hypothesis as 0, only when it lies on the upper tail as shown in the figure below. So in this figure we again have the normal distribution of x bar, we have the density function of x bar, but now our area of rejection is the upper tail and we have denoted it as 2.5%, which is the upper tail. Now we could also perform a 5% test by just increasing this rejection region to that extent. Note that alternate could have another possibility where mu is greater than mu 0 or mu is less than mu 0. These are clearly one-sided tests, and it would be appropriate to consider the right and the left rejection region respectively for any conclusion. Thence, the principal reason for applying one-sided test should solely depend on the relevant question, theory and economic sense, and which is an example in our third case. The procedure for a two-sided test is as follows. We are saying for a two-sided test, your first step is set the hypothesis, the null hypothesis as 0 equal to mu 0, and an alternative hypothesis as mu not equal to mu 0. Then calculate the test statistics T, which is distributed as T n minus 2. The third step is, given the level of significance alpha, find the critical value under alpha by 2 and across the degree of freedom. Call it T star. The fourth step is that if T, which is the T calculated, is greater than T star, reject the null hypothesis. This implies that mu is significantly different from mu 0. And the last step is the null would also be rejected if the probability p value is less than this alpha, the level of significance. Similarly, let me share with you the procedure for one-sided test, and is as follows. Many of these steps are similar. The first step is set the hypothesis H0 or H0 mu equal to mu 0, but now the alternative hypothesis H1 is mu greater than mu 0. The second step is the same, which is calculate the test statistics T distributed as T n minus 2. The third step again is the same, that given the level of significance alpha, find the critical value under alpha and across the degree of freedom and call it T star. So the third step is similar to the third step earlier. Similarly, the fourth step is also similar. If T calculated is greater than T star T tabulated, reject the null hypothesis in favor of the alternative and conclude that mu is significantly greater than mu 0. And the last step is also same, that if the above alternative was set as H1 where mu is less than mu 0, then we would reject the null hypothesis if T is less than minus T star. So let's conclude this module by looking at an example using both two-sided and one-sided tests. This is our example 4. In this given model with total number of observations as 20, we define p hat equal to 2 plus 0.90 W. The standard error for alpha is 0.10 and beta is equal to 0.05. Suppose we want to see if the price inflation and wage inflation rate is the same at 1. Thus we set the hypothesis as S0 equal to beta equal to 1 and H1 is beta is not equal to 1. This clearly is a two-sided test. Now calculating T statistics as T equal to 0.90 minus 1 upon 0.05, this comes out to be minus 2. The critical value at 5% level of significance with 18 degrees of freedom, which is Tc, is equal to 2.1. Therefore, you find that modulus T is less than Tc. Now, according to the rule, we do not reject the null hypothesis in this case. The estimated parameter has a coefficient less than the hypothesized value, but according to our test conclusion, the difference is not significant. A two-sided test does not reject the null hypothesis. Nevertheless, there could be a possibility where the rate of price inflation is less than the rate of wage inflation. Now, one plausible reason for this to happen could be increase in productivity. Certainly, it will lead to the other way around. That is, make the rate of price inflation more than the rate of wage inflation. So how do we know that? In order to know that, we reiterate the difference between the two tests. Let's perform the one-sided test now on the above example. So our new hypothesis now becomes S0 equal to beta equal to 1, but alternate hypothesis H1 now is that beta is less than 1. Now, with no other changes in the estimated model, t statistic remains at -2. But the critical value at 5% level of significance with 18 degrees of freedom now becomes Tc equal to 1.73. As you can see now that modulus T is greater than Tc, we can therefore reject the null hypothesis and conclude that coefficient of wage inflation is less than 1. That is, the rate of price inflation is less than the rate of wage inflation. Therefore, the above result can influence us to say that one-sided test has an edge over two-sided test. However, one should refrain from making such statements, as even though the possibility of beta greater than 1 can be excluded, the possibility of beta equal to 1 cannot be excluded unless we test for it. The statistical significance of a parameter depends fully on this T statistic, and the economic significance depends entirely on the magnitude of the regression coefficient and its sign. While concluding about the estimated model, one should be careful not to emphasize too much on either of these two. A variable can be economically significant but not statistically. There could also be a case where a variable could be statistically significant but not much relevant to the estimated model. Researcher therefore has to be very careful in finding a middle ground and at last presenting her concluding remarks. So let's summarize what we have learned in this module. So dear students, I am sure over these last half hour you would appreciate we have learned about hypothesis testing, that how it is the vital part of econometric analysis. We have also learned the tests explained in this module are associated with the simple linear regression model and form the foundation for the more general multiple linear regression model. Similarly, we have seen that significant result does not mean important, it simply emphasizes on statistical significance. Now, apart from having a sound knowledge of the terminologies like type 1 error, type 2 error, one-sided, two-sided tests, etc., it is also important to know how to present the results.